this week and another for the previous week. And then we will discuss a topic, okay? In the name of God, session 12. As I said before, in the previous session, started talking about clustering and classification. We reviewed two methods in the and this issue passes in reference B and on the page of 17.7. This topic started as you can follow all the materials in this and it is the authors of this book expand topics in so here. Okay. In the previous session, we discussed about the comments. If you remember, of this chapter, studied and type of unsupervised data mining, feature extraction, and like this. We explained this before, and then after that we talked about comments, and then we analyzed like dendrogram. Okay, and according to now we want to talk about a Gaussian mixture model and expectation maximization algorithm. Consider that have some data like this in this dot, and we call it X. Our data is we want to fit a Gaussian model to this data, and our goal is estimate the parameters of this Gaussian distribution. Okay, for example, in this figure, you see that we fit two Gaussian. Okay, and as you know, the two parameters for Gaussian distribution is mean and variance. Enough and the variance around mean. Okay, we called it theta, all the theta in totality. Okay. Another thing is that we must know the number of this distribution. For example, in this data, we know that we considered two classes. Then, when distribution, we must consider two means and two variance. Our goal is clear. For example, this is the data. Okay. At first, we guess two variants. You know the concept of mean and variance, and we explained before in PC analysis. Also, then we have a statistical data. We first initialize to Gaussian model, and then we iterate this date. After that, we update the variant by expectation maximization algorithm. How it updates, we have math in the book. But our way is that, again, I repeat it. At first, we have some data. We initialize the Gaussian parameter for Gaussian distribution is mean and variance. By L of B is variance. Okay? For example, the EM by attention to data distribution, update this to Gaussian model. Update in the edition of 5. Then update. Okay, then update it. And you see, after 15 iteration, after 25 iteration, we have a two distribution, two significant distribution, that there are many differences between this green and this. Okay, again I show it. We have this data. Here is the mean and the variance, and by using, we update parameters, update the mean and the variance. You see here, the mean changes, the location changes. The variance changes around the iteration 5 update. Then it's updated. We have this. After 25, we have this. And now you see that the differences between 25 and 15 is less than the differences, for example, between iteration 10 and 15 is so differences. But between 15 and the 25, they are similar to each other. Then in this iteration algorithm, okay? Then totally, if we want to review this Gaussian mixture model, we considered the Gaussian distribution for data, and for the Gaussian, we have some parameters. We called it theta. Theta contains the mean and variance, and then we weighted these distributions. For example, for this example, we have two classes. Then we have alpha 1 and alpha 2. And we consider that the summation of this alpha I is equal to 1. Then totally, if we have call classes, the weighting of this equation is equal to 1. Okay? Okay. And then after that, our goal here is to know about this theta and this alpha. How we can access this by maximization likelihood recombination. Please assume observed specific model that we have data. We assume this, formulate some parameters for that model. Then we calculate it. This step is expectation step, and then after that, in a specific iteration, we update the parameter. We maximization we update the parameters to achieve the most differences between two classes. Then we iterate it until we converge to our goal. Okay? And as we see, we don't know how to model the missing data, how to determine the number of Gaussian mixture. For example, we must, it is like co-means. We must know the number of classes. And then the parameters estimation for Gaussian mixture is hard. And what model to be used is another difficulties. Okay, any questions? Okay, you write something. Naima said, is this the second part of the cluster? Yes, as I said. And then Ahmad said that, do we have programming in? Now you ask this, Ahmad. Yes, as I said before, after we finishing this topic, we have exercise. Our exercise is a program, okay, using these references. Now we review the book. As you see, here the EM works, we have these but course, in this course, this formulation you must learn it. But the most important of learning this equation is that you know how to program this and how you classify the data using Gaussian mixture model in MATLAB. Okay, in this book we have the MATLAB code. You can copy paste these codes and then see the results. Step by step they explain about the classification. Okay. Integer is alright, typing. Okay, you continue. What difference between Cummins and EM algorithms? They are completely different. Let me to open the comments. In comments, who ask انتظار ask. In comments, the previous slide is better. In comments, you specified two initial means. Only you specify the mean of two data. The similarity is that for both of the comments and EM, you must know the number of classes. Okay, but the differences is that we don't have any constraint about the distribution of our data in comments. But in EM, we considered, we have some constraint that we assume that our data has the Gaussian distribution. Okay, but in comments we don't have this assumption. Okay, and then in comments another differences is that in comments we calculate the distances between each data and the mean. Okay, and then we try to minimum these distances. Okay, but in EM we try to have two classes. The concept of these two are different. Okay. For example, in comments, here we initialize page. Okay, you said okay. We initialize the mean. We calculate the distances. We iterated that we don't have any differences in the distances. Okay, they're completely different. But the goal of all the clustering is similar to each other. The goal of all of them is that we classify, we separate the data that the similarity in each class is high, but the similarity between class is low. The goal of all of the clustering is this and classification. Okay. Another thing of clustering, another method is another supervised learning is that linear discriminant analysis. What is this? This is also very interesting method and very applicable. Again, consider this data. Consider this data. You can project using before the projecting. You can achieve. You can obtain the eigenvectors of this data, the principal component of this data using the PCA. And then you using this principal component, you can project this data, for example, to this direction or to this direction, or okay. And then now, after the projection, please consider the data distribution. The differences between the data distribution between the green and purple data, the differences in direction 1 is better or the direction too. Differences between in the second projection is much clear. You can separate this projection to two classes, but the overlapping in the first projection is high, and in contrast, the overlapping between the two classes is low. The second projection is better. Then the second projection is better. And because in this method we want to find the best line for the projection, we called it linear discriminant analysis, LDA. Okay. Now, behind this concept, there are some mathematical equations. Okay. Again, consider a set of n-dimensional samples. We have subset of called a subset of the data D1. We labeled it with W1, and another subset is T2 with the label of W2. We want to project the X to another space, to another line, okay, to find new data, that we can classify it in a simple way. Okay. Now, and it is better I said that, then we want to find this W. It is questions for us. What is this W? How we can project X to Y? How we can transform X to Y? Okay. According to our main goal, we want to have the high similarity in each class and low similarity between classes. Okay. Then the researchers said that, okay, we consider this a ratio, okay, and in this ratio, W, don't note the W at first, but we can calculate SP and SW. SP is related to the scatter matrix between class, and SW is related to the matrices within class, in the class. And also, if you attention, SP is related to the mean of the two classes, and SW only is related to the one class. Okay. Then after calculating the SP and SW, we put it in this equation, and according to the previous discussion in SPD, W is and SP is related to eigenvalues and eigenvectors. Anyway, we can calculate W, and after calculating this W, we can transform X to Y, and then we can classify it. Okay. Of course, the details of LDA is much this discussion. But as I said, the concept is important for us because we want to know the concept of different clustering, and then after that and the differences between them, and then after that we want to run it and classify any data in MATLAB. Besides this concept, we must know that comment in the MATLAB. Okay, and again here you can run the MATLAB code because why I myself run it, okay, but why I don't run it in our online class, because it is so simple. You only must copy these codes and paste in MATLAB and see the results. Besides the simple way of this code, another goal in my mind is that you yourself also do this, and then you can change the parameter and see the results. Okay. Another method, and it is also a supervised method. Any questions? Another method is that support vector matching. What is support vector matching? Again, consider this distribution, these data distributions. Okay, they labeled white and black. You have white and black data. The label of one of them is 1, another one is -1. Okay, black is 1 and white is -1. And again, we want to classify it. Okay, but we don't know at the first time. We don't know what is the best classification, what is the best result of this classification. And for example, in this distribution also, we don't know about the distribution of this data. Maybe according to a specific application, we can consider the distribution. Okay, but totally in this slide we don't know. And also we want to introduce support vector match. Okay. If we want to have a linear classifier, okay. For example, we can consider this line. Okay. Another one said that this line is also good. It seems that this line is good. Another one said, okay, this line is also good. Anyway, we can consider many lines. Which of them is good? Which of them is the best? Which of them is the best? For example, in this line, in this pink line, this data is so near to this line. But for example, in this line, there are 4. Then maybe this line is better. The second is better. Okay? But we guess by the mathematical result. We don't know what is the best. Okay? In the support vector machine, in addition to the line, they consider margin to this line, this orange. Consider the orange area around this line. Okay? If we consider the margin around this line, then maybe we can decide better that which line is better. Okay? Oh, sorry. For example, for this margin, this black data is this margin. If we increase the margin and also consider another line, we have we have larger margin. Then this line with a large margin is more reliable compared to the previous one. Then this is better. The maximum margin linear classifier is the linear classifier with the maximum margin. This is the base of support vector machine. Okay? This is the base of support vector machine, and because we have the linear classifier here, we called it linear support vector machine. Okay? Then we want to specify a line and margin. Okay? Our goal in the support vector machine is specify this line and this margin. Then because it's linear, we consider equation. For example, wx plus b is equal to 0. It is a line of classifier, and the margin of upper margin, we consider this equation is equal to 1, and the lower margin, we consider this equation is equal to minus 1. Okay. And then this blue area, and this area is greater than 1, and this area is less than 1. Okay? Totally, I can say that we consider the area between two lines, between these margins, and then we can obtain this equation. Okay, and this equation W is, we don't know the W, we don't know the B, only we have x. X is our data. And because of this, in the previous slide, we said that, okay, we want to find this f, okay, and this sign is related to this margin that I explain it here, okay. Then again, by equation mathematical, we can find this w and this b. How we can calculate it? In the book explain. The book explain about this. As you see again in these figures, explain about the line, about the margin. According to the data, we can decide which line and margin better. Okay, according to the data, we can set that. Again, it explain it and then set that by some optimization algorithm. Using some optimization algorithm, we can find the W and B. And as you see in the book also, they explain totally, not very in details. Only said that, okay, we can calculate it by optimization problems. Because in MATLAB, you can write SVM, okay, and you must only define the parameters, the input of this SVM. But what is the input? What is what we can the best input? We must know the concept of this, and then because of this, we explain it. Okay. Another thing is that, as I said, this is a linear SVM, but we can have a non-linear SVM, and it means that instead of processing the data directly, instead of processing in a direct way, we map the data to another space, and then according to this new space, to this new mapping, we classify. We map X to phi X. We transform X to another space. Okay, this phi called the kernel, and we can have linear kernel, non-linear, RBF, and different. We can quadratic kernel. We can select different kernels. Okay. And in the book also, you, for example, consider this. For example, here, if you have x1 and x2, and you want to map and transform this data to another space or coordinate. For example, you can consider z1 as x1, z2 as x2, and z3 is this. And this is a considering polynomial of the data. Okay, and then after that, according to the classifier and to the margin, you can classify these new data. Okay, and here it explain it as I see, and here we said that the kernel function is defined using 5.39, and again using we can access and we can achieve the weighting and align. And for example, it is a radial basis function RBF. Your kernel could be seen like this, or polynomial kernel. And also again, you can see the SVM classification as MATLAB code in this book, and you can copy paste it in the MATLAB. And another classification is random forest or classification trees. In the previous session, I explained it, but with a different name. When we want to explain about this hierarchical clustering, we said that we can classify it from bottom to up or from top to down data. When we wanted to classify it from the bottom, we consider the features of its object, and then we join them according to the features, and after that according to all constraints, for example maximization, averaging, or like this, we join the groups, and then step by step we continue our processing. But the top down is the construct in the inverse of this processing. From the top we start. For example, this is our data. We must search how to separate the data, and we, after seeing all the data, we separate it into branch, and then again after that according to our constraint or our assumption, we repeat it and then see this class, and we divide it, for example, to 3 or to 2, of course to 2, and then we continue it, and this is from top to down, and we continued it until we have the most differences between the classes. Okay. In this book we called it classification trees, because it is like a tree, and random forest. It is like this: divide to green and orange, purple, then again divide the orange and purple to classes. Okay, and it is like this. Okay, and at the last subsection, the book said that the top 10 algorithms in data mining in 2008. And it explained that in December 2006, there is a paper that explained the top 10 algorithms for data mining, introduced these algorithms here, and in this year, and in this year 2006, the deep learning didn't use as much as these days. Then, as you see, they don't contain these top 10 algorithms don't code contains deep learning. Okay, and again in 2 years after that they updated and then introduced some the famous top 10 algorithms in data mining, and they only introduce in the book the methods. Some of them we explain. Also, you have the details in these chapters. Some of them we don't have. If you yourself want more details, you yourself can follow and search about it. Anyway, the top-down algorithm is Cummins, EM, support vector machine, a classification and regression tree, and in the parentheses you can see the MATLAB codes. Nearest neighbor, it is similar to Cummins, but we also must know the number of neighbors. And Bayesian models, Adabus, C 4.5, a priori algorithm, and page rank. We explain some of them, or we didn't explain others. Okay, thanks for your attention. If you have any question, please ask. You don't have any questions? Okay. Okay, then we finish this session. Thanks for your attention and participation in the class. And good afternoon. Another thing is that the number of students in this class is so low. I don't know why. Please inform your friends that they submitted in this course. Follow the PowerPoints, the videos, online and offline in the LMS. And from the next week, also we have the exercise. And as I said in the first sessions, we don't have any special quizzes except after final exam. We have the exercise and the MATLAB exercise. Then you must do it. I will upload it now. I will upload it in the LMS now. After each online class, I upload. Okay. Any questions? Okay. Then wait for the offline videos. I will upload it through. And wait also for exercise. I will upload this in this week or in the next week. Okay. Good afternoon and good luck. Bye to all of you. Bye. And in your language, I said that fi amanillah, and in Persian, I must say Khoda Hafiz. In French, I must say au revoir. Okay. Thanks. Bye. Thank you. Bye.